My friends, good evening. It is literally Christmas Eve. I brought an apple, I brought a knife and a plate, right? And what are we going to do today? The purpose of the video is to explain the navigation elements that justify using certain units in aviation. Today we'll discuss the nautical mile, also called the sea mile, and the knot, a unit of speed. There are a lot of people, pretty much since I started this channel, who tell me every time, for example, when I mention something in a video, there you go. The plane touched down at 140 knots. They ask me, why do you use knots? Why not use kilometers per hour like everyone else? And for distances, why use nautical miles? Use kilometers. It's simpler. Actually, kilometers and kilometers per hour are not used at all in aviation, except in some places in the world. But overall, we use nautical miles for distances and knots for speed. By the end of this video, you'll understand these units, understand their reasoning, and know why we use them. So I take an apple, okay? And I'm going to cut it in half using this knife. So I took a very minimal knife for the task. It's not very sharp, okay? Whenever I use a knife, I always take the least sharp knife, but one that can still do the task I want to do. Same for tools. For tools, I always take the least powerful one. Someone who can do the job. Why? As the Germans say, we all have trimpeltiers at home. Yes, that's the main point. Secondly, the difference between a good and a bad knife. That's the difference between, do you happen to have a Band-Aid? And then, do you know how to make a tourniquet? There you go. That's the difference, right? That's why I'm always in favor of minimalist knives. So here we go. I'm going to cut the, wow, I was about to say the pear, but it's an apple, the apple in half. Careful, here we go. I'm cutting the apple in half. I've cut my apple in half. There you go. So by cutting the apple in half, let's imagine it's spherical, okay? That's important. We can't talk about it any other way, you know? Here, this is going to represent the Earth at a certain point. We are talking about an Earth that's in this form. It's not made of spheres, right? The Earth isn't like that if you want. All right, okay. If you assume that the Earth is a plate, it's kind of a flat disk like this that floats around in space. Everything I'm going to tell you will be false. All my navigation will fall apart, all right? We won't be able to navigate. It won't be possible. When we cut. But, you know, times are tough, right? Really, times are tough. I understand people who say the Earth is flat. Do you know why I understand them? We've reached a point where we may have lied to people too much. There's so much of it. A loss of trust. Nobody trusts anyone anymore. That's what's terrible today. And because people don't trust, well, they start to question everything, right? Including, yes, well, there you go. The Earth isn't round. That's what we've been told. But, you know, maybe they lied to us, right? The important thing is to trust at some point. We can't. I know that I'm guilty myself of straying from the official version sometimes. I'm not better than anyone else. I'm not hiding it from you, but I think sometimes there are people who push things. Let's get back to our story. When do we cut? When you cut a ball like this with a plane like I did, you get a circle. All right? The intersection forms a disc, a circle. You can see the circle here. I'm not sure if it's clear. And what we call a small circle. I'll show you the opposite of a small circle. All right? I'll show you something else. I'm going to cut my apple again. There you go. And look what I got this time. I got a big circle. All right? So small circle, big circle. Careful, the light. There you go. Is the light working or not? No, it was working. So the big circle, if you want, is a circle that will always include the center of the object. If the plane passes through the center, we have a big circle. We can cut however we want, all right? We can cut. If I take this one, we can cut it anyway. What matters is we cut and provide a plane, which passes through the center of the Earth. We get what is called a great circle. So small and great circles, that's the first fundamental concept in navigation. Now let's continue. We have the angles that we generally express. How do you express angles? In degrees. I brought a little one here. There you go. That's it. We have 90 degrees, a quarter circle, and a half circle, which is 180 degrees. We use degrees to describe these. How is a degree divided? How do we subdivide a degree? A degree is subdivided into minutes. These represent 60ths of a degree, and we also divide it into seconds, which are 36 hundredths of a degree. What we're interested in today, we're going to focus on the minutes of degrees, okay? 60ths of a degree. Okay, I'll make a quick drawing, won't I? Let's imagine that the person is at the center of the earth. A person is at the center of the earth. And then what he's going to do, he's going to define an angle with his arms, his hands, or his arms, if you want. So he can define 90 degrees, he can define 180. We're going to ask him to define an extremely small angle, which represents 1/60th of a degree, which represents 1 minute of arc. All right. So I'm going to make a little drawing with my famous notebook, very famous. Look. So now wait. Yes. I'm a little bit bothered. Sorry for the noise, careful. Since I don't need the knife, I'll wrap it up. I'm not waiting until the video ends, because I might forget. So I'm wrapping it up, I write knife on it. There you go. See, I write knife on it and drop it in the box. That way it's gone, but I'll pick it up later. But in the worst case, if I forget it, there's no risk of an accident. So what do? I was saying that I'm going to draw my land. It's a circle like this. I have my little guy who's in the middle, okay? Since my little guy is in the middle, all the great circles go through him, okay? The great circles go through him, of course. So I'm going to ask him to define an angle for me. I'm going to exaggerate my drawing, since if I use 1 arc minute, you won't see anything. The lines would overlap. So I'm just going to draw that, all right? Just that, okay? That's 1 minute. We'll mark a cross on Earth's surface. That's the question. It will make a cross on Earth's surface. So let's see what happens. We assume that the Earth is 40,000 kilometers in circumference, okay? 40,000 kilometers in circumference, and we'll do the calculation. So I take my calculator. I'll show you something. So I take my 40,000 kilometers that we could see here. First, I divide by 360 to know how much we have in 1 degree. What is the arc intercepted by 1 degree? So 1 degree equals 111 kilometers, right? And if I divide by 60 to find out the arc minute, that's it. It's 1,851.8. So I'm going to, let's say, 1,800 seconds per kilometer, or 1,800 seconds per meter. So what it's going to intercept, it's going to intercept the surface of the Earth. It's going to intercept a length of 1,800 seconds meter. That's what we call the nautical mile. The nautical mile, or the sea mile, is 1,800 seconds meter for this reason. In fact, it is defined as being a nautical mile. The distance intercepted by an angle of 1 minute of arc at the center of the Earth, which extends to the surface of the Earth. All right, so now if we look, what is it? What is the benefit? I'll give you a very simple practical aspect. I'll give you a practical aspect. Look, a simple practical aspect. For example, I have my Earth, which I always show with my big circle like this. And you notice, for the flat earthers, that all my reasoning is dead. All my reasoning falls apart. If my Earth is not shaped like a ball, so I do this, there you go. So this is my Earth, this is the equator. The equator is an example of a great circle. The equator is a great circle. In general, the parallels are not great circles. For example, if I take the polar circle at about 66 degrees, okay, north or south, or if I take the tropics, okay, well, these are parallels, but they're small. You notice that they're small, so only the equator is a great circle. If I use the meridians, like the Greenwich meridian at 0 and the opposite at 180 degrees, for example, this one is called the dateline. It forms a great circle for me. All meridians are parts of great circles. So let me show you something. I'm going to show you latitude. So let's take, for example, a first angle here, all right? Let's take another latitude here. For example, if I have 41 degrees, 41 degrees, 41 degrees, that's Barcelona. That angle is 41 degrees, all right? It will be represented on a map by lines. If I use a Mercator projection, it will give me straight lines. So notice what I can do. One thing I can do. Let's say, for example, I have here on a map, I have 41 degrees here, and I have here, for example, 42 degrees, okay, of latitude. You see what I can do? I can take a compass. Okay? And I can say this. I don't even need to know the scale of the map. I can say that the distance between the 41st and 42nd, I can say that this distance you see here, this distance I just defined with the compass, this distance corresponds to 1 degree. 2 great circles. What does that correspond to? That's 60,000 nautical miles or 111 kilometers. Just imagine 1 kilometer. So it's 60,000 nautical miles. If I do this, I can say I have 60,000 nautical miles between these points. Why? Because the scale of maps, in general, the scale of maps is the same in all directions. Do you know why? Because you can think about that, you can meditate on it. If the scale wasn't the same in 2 different directions, the map wouldn't preserve the angles. Well, yes, of course. So, see, the thing is, if the scale of a map isn't the same, because maps, you know, there are lots of projections. There's Ambert, Mercator, there are polar projections and all that. There are straight projections, oblique ones, and so on and so on. People have always tried to represent the Earth, which is a sphere on a flat surface, which is a map. You can't walk around in a cockpit with a sphere. It's just not possible. Besides, to be honest with you, navigation has lost its prestige since the advent of modern airplanes. People don't do that anymore today, do they? Pilots aren't going to navigate like they used to back in the day. On the Titanic, all that is over now. Today, they have flight plans that are programmed into computers. These are points that have names, except over the oceans, where maybe we've kept the tradition of giving them geographic coordinates. But in reality, everything I'm telling you is actually disappearing. Many people study this quickly just to pass multiple choice tests for an airline transport pilot license, private pilot license, or similar. And then once it's done, well, it's behind them, right? Unfortunately, all those things get lost. So I'm telling you a story that among the desirable features of a map is to have what? It's about keeping the scale equal in 2 opposite directions. Look, for example, I take my point A and my point B, which are here, okay? And for example, let's say I take a point C, which is here, okay? Let's say A and B are at the same distance. A and B are at the same distance. So the angle between... The angle here is 45 degrees, obviously. It's half. Okay, obviously, you can see that. Now, let's imagine that my map doesn't have the same scale in 2 different directions. What is it going to do? Let's say A is here, and B, even if it's at the same distance, is here, since the map doesn't have the same scale. So if I take point C, which is here, for example, which is north of B and east of A, it will have an angle that won't be 45 degrees, it might be 30 degrees. Okay, so maps that don't have the same scale in 2 different directions won't preserve the angles. A map that doesn't preserve angles quickly becomes useless for navigation. Great circle is shown in geometry, but I won't do it. It's demonstrated that the closest point, the shortest distance between 2 points, the shortest distance between 2 points. On the Earth's surface, it always passes through a great circle. So that might be shocking. It might be shocking. I might not understand. Someone might say, yeah, the great circle is the shortest path between 2 points. Yeah, the great circle, the section of the great circle, and the shortest path between 2 points. Exactly, not the small circle. So that's actually what we call orthodromic routes, orthodromic paths, which are routes that always follow, the routes always follow arcs of great circles. And if you look, for example, if you look at a projection on any map, you'll see a plane, for example. Let's say it leaves from here, it leaves from London or Paris, okay? It leaves from Paris and it's going to a city in the south. Let's say it arrives in Chile, for example, okay? You'll see that it will do this. You'll see that the great circle routes, the routes are always segments of great circles. And the great circles on a map, on a cartographic projection, well, what they're going to do, they will always, their concavity will always face the equator. All right, that's why you're going to see this S when the equator is crossed from side to side. That's why if you take a plane between Paris and San Francisco, you'll see that it will go as far as skimming over Grand Highland, as you say. But why does it do that? It's because it follows a great circle, so it must be a great circle. If we take Paris, we take San Francisco, and then what do we take? The third point, what is it? Paris, San Francisco. The third point is the center of the Earth. The thing to do is to know it, that's all. Go outside. Paris is set since that's where the plane is, and Los Angeles or San Francisco are set because we sold tickets there. Earth's center is defined by geometry. The other points are fixed, leaving us no choice. And so you'll see that the plane goes up toward Grand Highland, and then it flies over northern Canada, Labrador, all that, and then it comes back toward the United States. And when it enters the United States, it comes from the north, it enters through Canada, and heads on a course relatively toward the south. Actually, okay? So it's just to explain a little bit what it looks like later on the ground. We've covered big and small bags and learned about the nautical mile. So what is a knot? For example, instead of saying miles per hour or nautical miles per hour, we simply say knot. That means if we have any vehicle that does 60,000 per... All right, if it covers that distance per hour, we won't say it does 60,000 per hour. We'll say it does 60 knots. So the knot is specifically related to navigation. It's also connected to nautical miles and all that. So if we take our map, we can actually use the speed, using the speed in knots. We can find out how many miles are covered along a great circle. And from there, we can figure out, we can make an estimate, how long it will take to reach the destination, how long it will take to cover such and such a distance and all that. All right? So all these units are connected. If you prefer kilometers, I can help you reason in kilometers if you prefer kilometers. So we use the same reasoning for kilometers. But then be careful, we won't be talking in degrees, but in grads. The grad, a full circle is 360 degrees, which equals 400 grads. Okay, 400 grads. So if I take the Earth and say that the Earth is 40,000 kilometers, I put my guy in the middle of the Earth. I ask him to open his arms, not at an angle of 2. A 60th of a degree or a minute of arc, I ask him to open his arms to 100th of a grad. The grad is divided into centigrades and milligrades, not minutes and seconds. All right? So I ask him to do for me, I ask him to make 100th of a grad for me, all right? A centigrade. So he'll open his arms like this. We'll start at Earth's surface and intercept how much? You just have to divide simply. We have 40,000 kilometers, 400 grads, and then we're going to have 40,000 centigrades. All right, 40,000 hundredths of a grad make up Earth's circumference. So how much do we have? We have 1 kilometer, which matches the grad, and we measure in kilometers per hour. Okay? So you see, if you count in degrees, if you count the latitudes, the longitudes, and all that in degrees, you have to count the rest. The distances in nautical miles and the speeds in knots. Whereas if you count in grads, which nobody does here actually, you can count in kilometers and kilometers per hour, but you also need to have maps that are marked in grads. I've never seen one. I think they might exist, but I haven't seen one up close, all right? So there you go, my friends. That was just a little bit of theory to explain this story, wasn't it? Why do we talk about nautical miles and knots in aviation? I'll make more videos soon, and in the meantime, I wish you a Merry Christmas and Happy Holidays. See you very soon.